Hello and welcome to lesson 3.2. In lesson 3.2, we're going to kind of cover two main ideas. Okay, the first main idea is rational exponents. And so what I want to or hope to kind of impress upon you here is that really exponents and radicals, squares and square roots and cube roots and all that are the same thing. Exponents and radicals. They're the same thing. We just write them differently. They're a lot nicer to look at in one way or the other. Here's what I mean by that. If I were to take any root, let's just say a third root, for example, and I take any base, let's just let it be an x, and I raise it to any power, 5 for simplicity's sake. I can rearrange this to be nothing more than an exponent, okay? So let's label some pieces to help us keep up. This is the root right here. This is right now my exponent. And this x right now is my base. So keeping x as the base, I can rearrange something here. Let's see. So that's still the base. I can write this root as an exponent, a fractional exponent. That's why it's called a rational exponent. It's a fractional exponent. And this would be x to the 5/3. These two things are the same. Okay? Notice the root comes down to the bottom of the exponent. Bottom of exponent. And what was the exponent goes to the top. So get cozy rearranging these, because sometimes it's easier to work in one form or the other. So the root comes around and comes underneath here. Well, what if there's not an exponent there? So what if I have an expression like this? Like fifth root. We can do any root we want. The fifth root of x. Well, remember that there's understood to be a 1 exponent if there's not showing any, so we could always plop a 1 there, and I could write the fifth root as 1 to the 1/5, or x to the 1/5 power. Wait a second, do you remember last lesson when I had you do things like this? Third root, the cube root of x to the 6th, and I told you it's just going to divide this into by 3. It's just going to be x squared, but that's why. If I were to rewrite this, keep my base the same, the exponent, and the root comes to the bottom of here. Oh, 6 divided by 3 is 2. Okay, so that's really nice then. So I can turn radicals into fractional exponents, or if I give you a nasty fractional exponent, you can turn it into a radical, and you can go either way to make life simple. So let's just do a few examples with some simple numbers. So something like, could you figure out x to the 2/3? Well, that would be insanely hard to do, just sitting there and trying to calculate x to the 2/3 written this way. Well, what does that mean? Well, this is the bottom of the exponent, so that's the root. So this is, okay, so this is the cube root of 8 squared. Or I could do the cube root of 8 all squared. The order here doesn't really matter. For instance, well, what is 8 squared? 8 squared is 64. What's the cube root of 64? I believe that is 4. Oh, what if I wanted to do, like I said order doesn't matter. So could you prove to me order doesn't matter? Like if, let's pick it up right here in a different color. Let's take the cube root of 8 first, and we're going to keep it the square there. What's the cube root of 8? Oh, the cube root of 8 is 2. What's 2 squared? 4. Okay, so I can do these pieces in either order. I could square, then cube root, or I could cube root, then square. But like either way, I get the answer of 4. But this, turning it into a root, a radical expression, is much easier because I don't know what 8 to the 2/3 power is. I'd much rather turn it into a radical and then, oh yeah, I can square something. I can cube root something. I don't know how to raise it to the 2/3 power. So that's the potency or the power in this. We can do another one for just one more for complete kind of feeling good about this. What if I were to do something like 9 to the 3/2? Which one's the root this time? Oh, the 2. The 2's the root. So this is a square root. So this is 9 to the 3rd square rooted. I can put the 2 in to make you feel better, but I don't have to put the 2. Oh my, 9 to the 3rd power is going to be huge. But remember what I showed you here. Order doesn't matter, and I could take the square root of 9 pretty easily. What's the square root of 9? It's 3. So now I have 3 to the 3rd power. Okay, that's much easier. That is 27. So picking an order or doing either order. Now you also can easily use a calculator if you need to. It's not hard to use a calculator. You could have said 9 to the 3rd power and said, oh, that's 729. Oh my. And then I need to take the cube root of that. Desmos has one of these. See, I think I probably need to do the 3, then the cube root. Nope, it lets me put it in nicely. So cube root, let's put the 3 in there. And then, what was the number? 729. 729. Boom, and it gives me 9, which is hopefully what I got. I got 27. Did I mess something up? Oh, it's a, dang it, a square root, not a cube root. I did mess something up. So let's go back to that. Instead of, there we go, square root. 27, there, perfect. If I could only not make typos when I type in calculators, I'd have a better time at this, but I always make typos when I use calculators. That's usually why I don't use calculators. If you've ever been in one of my in-person classes, you know I am very famous for typing in the wrong numbers. So I apologize. But anyways, there's the first idea. I told you this lesson had 2 ideas to it. Rational exponents and that's the first. That was a very simple, fast topic, right? So now we want to dive in kind of to the next idea, which is, okay, let's look at simplifying these radical expressions. I'll go ahead and tell you, it may be easy if we use some of these skills that we've already learned, especially last lesson and this lesson already, to simplify these. But what we're going to want to do is simplify these rational expressions. And before I dive into actually trying to simplify them, we're going to give you 2 rules that are very useful. 2 rules, okay? 2 extremely useful rules. One is called the product rule, and the other is called the quotient rule, okay? These are both very useful rules for simplifying radical expressions. And here's what they are. The product rule says that if I have any type of root, say it's a 3rd root, and I have 2 things, let's just call them A times B, I can break them apart into their own radical expression. Now notice it has to be the same root. I'm not changing the roots, but I can break 2 things that are multiplied apart. Well, look here, this is an equal sign, so that's even better news, is that I can also go backwards if I need to. So if I have 2 different things that are both raised to or have the same radical, I can smush them together if they're multiplied. So I can break apart or I can smush together multiplications. Let me show you an example of that. That's like from last lesson when I would do something like, let's say I want to do the 3rd root of 27 times m to the 12. I think we did x to the 12, but I could break these apart into 27 times the 3rd root of m to the 12, and then I can handle each of these pieces separately. Well, that's 3. We know that's m to the 4. You could rewrite it as a fraction, or you could remember that I'm just going to divide this by 3. Okay, so I can break them apart, I can put them back together. That's cool. Sometimes it's helpful to put things together, sometimes it's helpful to break them apart. The quotient rule is very similar. It deals with, instead of a product, a quotient. So for instance, if I have something like the square root of 4 over 9, have you ever learned to do square roots of fractions? I know that just seems scary to me, but I can break apart over divisions like this. long as I keep the radical the same. This was a square root, so this is going to be a square root, this is going to be a square root. And I can go, once again, either direction. If it's easier to put them together, like say neither of these were perfect squares, but they would reduce, well, I might stick them back together and go this way. But if they, look here, they're both perfect squares, I'd rather be able to take the square root of 4 and the square root of 9. Well, then split them apart. I can put them together or split them apart. Same thing with multiplications or with divisions. So that would make a problem like this where I'm not so sure about doing a fraction, but oh, if I split them apart, oh, that's not what I meant to click on. I know that the square root of 4, I know that's 2. I know the square root of 9 is 3. That makes that much more doable. So I can be less fearful of fractions because of that. So let's do a few examples. Okay? A few examples and see how we feel about this. So say I give you something like square root of 50 over the square root of 2. Is 50 a perfect square root? No. Is 2 a perfect square root? No. Let's try putting them together, though, because they're being divided. They're both the same radical, so I could put them together. What is, well, let's just take the time to write it out. 50 divided by 2. Oh, I can handle that. 50 divided by 2 is 25, right? Oh, look, I know the square root of 25. That's just 5. So using this quotient rule, I can put them together to give me something much more simple. Okay. Or I could do, whoops, didn't mean to write there. Or I could do something like this. I could have something like the cube root of 3 times the cube root of 9. And I don't really like that because 3 nor 9, neither of them are perfect cube roots. But let's just try to put them together to see if I get anything better. So 3 times 9. 3 times 9 is 27. Oh, and we're lucky because 27 is a perfect cube root. That's 3. So I can put things together or pull things apart. It makes life much simpler. Okay. Now, let's kind of take this to the next step. This is where some students get frustrated, but I think this is a really neat next part. What if I wanted to do a square root of something that wasn't a perfect square root? But I'd like to simplify as much as possible. Like on the top of that fraction, we had square root of 50. That's not a perfect square root. But what we're going to want to do to be able to simplify these is I would like to square root as much of this as I can. So let me ask you a question. Is there any way to write 50 as a square root times another number? Is there a perfect square root that divides evenly into 50? And hopefully you're like, yeah, 50 is just 25 times 2. So you would agree 50 and 25 times 2, so this is equivalent, what I have written in white and what I have written in green. I did not do anything earth-shattering there. I just rewrote 50 as 25 times 2. Well, using this property that we just learned, I can split these apart, right? They're being multiplied. I can give them each their own radical. Well, that's cool and all, but what does that gain me? Oh, well, that lets me take the square root of 25. I know that's just 5. Well, can I do anything with the square root of 2? It's not perfect, no. But this is considered simplified and proper. This is not considered simplified because there's some square root in there that I can keep, I can take. Okay, so we want to get as much of the square root pieces out of here as we can. So we rewrite them, break them apart, and square root what we can. So this is 5 times the square root of 2. So does that make sense? It's an interesting way to simplify things, but it helps us to reduce or simplify down as much as we possibly can. So let's do another example. We'll do one with a third root. Third root of 24. So this is where it's good to know your squares and your cubes. Like I said, you really probably should have a piece of paper of perfect squares and cubes. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. If I did cubes, 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, and you could use a calculator to fill in the rest. So 24 is not a perfect cube root. Do any other perfect cube roots divide evenly into 24? Oh yeah, 8 does. 8 does. So I could rewrite 24, since this is a cube root, as 8 times 3. 8 times 3 is 24. And then I could break them apart because I'm allowed to break things apart over multiplications and divisions if I had a division. And then I could do the cube root of 8. Cube root of 8 is 2. And I'm left with this part in there. Okay, nice. Okay, so is that all that difficult or nasty? No, it just takes some getting used to breaking things apart to get a perfect cube or a perfect square. Can I do this with x's and numbers? And the answer is yes. So earlier in lesson 1, we did square roots of numbers and variables together. What if I wanted to do something like this? Okay, the square root of this. Well, 32 is not a perfect square. X to the 15, that's not even. Remember I said we would just half it? That's not a perfect square either. I can't just half it. That'd be 7.5. So let's see if we can break this apart. The first place probably is, let's just break this apart into 32 and x to the 15 so we can kind of take these piece by piece. Okay, let's just split them that way. So 32, does any perfect square divide evenly into 32? Oh, 16. So I could write 32 as 16 times 2. Alright, now let's look at x to the 15 here. I got an idea. Maybe instead of doing this, we could use that stuff that we used earlier in the lesson. And maybe we could just write this as a fractional exponent. Because there's no root shown here, but we know it's understood to be a 2. Put that like that. Okay. Can we reduce this fraction down some? Can we write this as a mixed number from back in middle school? Well, 15 divided by 2, what is that? That would be 7.5, right? So let's break this x up. Well, we can go ahead and break that up too. Let's break these pieces up. So I have the square root of 16 times the square root of 2. And I'm going to go ahead and break this x up into x to the 7th times x to the half. Because that's the same thing as x to the 7th halves. So x to the 7th, x to the half. Okay. Well, look at this. X to the half, that's just the square root of x, right? And square root of 2, so those pieces, yeah, they're not going to get square rooted. But let's see. Square root of 16, that's 4. Square root of 2 is still square root of 2. X to the 7th, that's just x to the 7th. And let's rewrite x to the 1/2. That is just the square root of x. Okay, wait a second. This is all multiplication. I could rearrange these things. Let's put the non-square root pieces out front, and the square root pieces, I can put these together. So if I put them together, let's see what I got here. I got 4x to the 7. And still in the square root here, I have 2 times x, 2x. Okay, well, I'll go ahead and tell you that was the extremely long way of doing it. But I really, really, really wanted you to see everything all worked out like that. Okay? Really wanted you to see really everything that we possibly could. All the details, all the really the minutia of me doing all this thinking, because nobody that I know of actually shows all these steps. So can I do this faster? I love trying to do things faster. First off, before you try it faster, you have to understand what I've done here. Okay, so rewatch this part of the video as many times as you need to fully understand it. Second off, if I just look at this, let's redo the same problem. Let's see if I can handle it faster. Okay, so square root of 32x to the 15. Okay, well, I'm still going to have to try to break 32 up. I'm still going to break that into 16 times 2. Okay, but x to the 15, I could write that as x to the 14 times x to the first power. I don't have to show that. And then I have these pieces that I can do the square root of, and these pieces that are going to stay in the square root. I'll do these in yellow squiggles. So, for instance, what's the square root of 16? 4. What's the square root of x to the 14? Remember, you just half it, x to the 7. All right, what pieces stay behind? 2 and an x to the first power, or just an x. Okay, that's much faster, but it's technically all these same processes that we did up here, just much more streamlined, okay? So if you can understand this, I would like you to streamline your work so that it's not insanely difficult for you to kind of, I don't want you to struggle with it and it to take forever. Let's do a cube root one. I may grab these to take with me for the next page. Control copy. Control paste. There. Let's do one last kind of example here with like a cube root, just to get a good feeling of this. Cube root 54 x to the 6th, y to the, let's go with y to the 10th. Actually, let's go y to the 11th. Whoops. Y to the 11th. Okay, so 54 x to the 6th, y to the 11th. So I'm taking a cube root this time, not a square root. So is 54 a perfect cube root? No. Do any of these numbers divide evenly into 54? 27 does, doesn't it? 27 times 2 is 50. Okay, that's good. Let's go ahead and take the time to write that out. Okay, cube root, that would be 27 times 2. Okay, so now it's a cube root, so I'm wanting to divide these by 3. So 6 divided by 3, oh, that'll work. I'm just going to leave that alone. X to the 6th. Does 11 divide by 3? No. So if I did divide 3 into that, I would have a remainder of 2, right? So but here's what I'm saying. Think about this. If I have 11 y's, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and I purposely wrote it this way. Notice that I have 3 groups of 3 and then 2 left over. So if I was trying to divide something by 3, I could divide into 3, and I would get 3 with a remainder of 2. That's one way of thinking about it. The other way I think about it is, what is divisible by 3? 3, 6, 9, 12. Okay, 12 is past it. So 9 is my best bet. So I'm going to rewrite this as y to the 9th times y squared. If you know your exponent rules, y to the 11th is the same thing as y to the 9th times y squared. Okay? Because 9 plus 2 is 11. Okay, so I break this part. Now that part is divisible by 3. So I can now jump to my answer part. Let's see. So what pieces in here are perfect cubes? 27. What's the cube root of 27? That's 3. 2 is going to stay in. So I'm going to use that one. That's staying in. Let's see. X to the 6. So 6 divided by 3 is 2. So x to the 2. Okay, we use that one. Y to the 9. 9 divided by 3 is 3. So y to the 3rd. We've used that one. And then last, y squared is going to stay in because there's not another group of 3 in there. All right, so what's still in here in the cube root? 2 and y squared. Okay. So there we go. Now, if you think any of this is confusing, kind of soak in parts of this lesson. Like, take a little bit of time, think about it, process it. Try the homework. Remember, you can repeat a lot of these questions as many times as you need to until you feel a little bit like you're understanding it. And email me if you have any questions. Okay, I know that this is a lot to soak in right here. This might feel overwhelming or look overwhelming, but I assure you, once you get it, once it clicks, you're like, that's not hard at all. I can handle that. That's not too bad. All right, good luck, and I'll see you next time.